No, Rajesh.
Okay. Okay. So yeah. So last time we talked a little about character theory. Yeah. So given a representation, we could define an invariant, which is the character of the representation. And basically it encodes, so for each element G of G, we get a linear transformation of the vector space. Yeah. So what it encodes is this trace of rho G. Yeah. And in the afternoon we saw that if this encodes much, in some sense it encodes everything about this thing it encodes the whole characteristic polynomial of rho G. That was one of the homework exercise problems. So just using this character function, you can write down characteristic polynomial of each of these rho G's. And then we computed. We saw that the character on the identity element, it takes the dimension. The value is just the dimension of the vector space. Yeah, because identity element acts as the identity on V, and its trace is just the dimension. Because it's the identity matrix, so trace is just the number of the size of the matrix, so to speak. And we saw that chi G inverse, the value of the character at G inverse is same as value of the character at G, and then take conjugate. Yeah. So here everywhere our base field is complex numbers. We also saw that chi G is a class function. So these are the three properties about any character we saw. And then we saw that character of V plus W is same as character of V plus character of W. And character of V tensor W, V and W are representations, is same as the product of their character of V times character of W. And for dual, we saw that the character of the dual is just character of the original representation conjugated. Yeah. And using these two and the fact that home VW is V dual tensor W, we get that character of half of it, some part of it is missing. Yeah. So character of home VW is same as character of V bar dot character of W, because it's isomorphic to V dual tensor W, and character of V dual is just character of V bar. Okay, so this is what we saw, and then we also computed the character of the regular representation. Yeah, so we saw that for regular representation KG, the character is has a very simple form. Yeah, so on identity element, it has to be the size of the dimension of this representation, which is same as size of G. And for any other element of the group, the character takes the value 0. So, and then after that, we saw Seus Lemma, which says that if we have a map between two irreducible G representation, a G equivariant map, then it's either 0 or an isomorphism. And so I have not written it down here. If these two irreducible, so if we think of this map as an endomorphism of an irreducible representation, then this map has to be a scalar times the identity. It can't be some random endomorphism. Yeah, it's a very simple kind of endomorphism. The scalar times the identity. So it's just multiplying by some number. Okay, so today we'll prove something called the orthogonality of the characters, which will help us determine any representation in some sense. So that will help us figure out a structure of any representation in terms of irreducible representation. So for that we'll start with some some definition. So let V1 and V2 be two representations of a group G, and let chi1 and chi2 be corresponding characters. Then we define a pairing chi1 comma chi2 within round bracket. This is defined to be 1 over size of G summation G in G, chi1 of G, chi2 of G bar. Okay. This will belong to, see, each chi1G is a complex number, chi2G is a complex number. You put a bar, it's a complex. So it's a pairing. So actually, this you can define it for any class function on G. Yeah. So remember, chi1 and chi2 are class functions. So on the set of all class functions, you can define it. Class functions on G, you can define it. Define this function, but in particular on characters. Yeah. So this works for this definition. Maybe I'll just make it a point here. So this definition for the definition, we just need this extends to. This definition extends to, excuse me. So the OneNote has frozen. This definition extends to class function on G. Class functions on G. So for all complex valued functions on G, which are constants on conjugacy classes. So we will use this bilinear map even for if we are given some class function f and f prime on G, we can define it, define this pairing. So also note that this is linear in the first variable. Yeah. So I mean, if you have two class functions f and f prime, so it's additive in both variable first of all. So you put it in left hand side or at right hand side is additive in both, and it works well with scalar multiplication on the left, meaning it's linear. And in the second variable is conjugate linear. You have to, so if you replace chi2 by some complex number lambda times chi2, then what comes out is lambda bar, not lambda. So it's conjugate linear in the second variable. Yeah. Another way to see what we have done is we have put chi2 G bar. Yeah. So another way to think of it is 1 over G, chi1 G, chi2 G inverse. Yeah, because chi2 G inverse is same as chi2 G bar. Yeah. So that's another way. And so you can think of at least for character when chi is a character. Yeah. So this formula works only when chi is a character. So maybe I should say if chi1, chi2 are characters, and not on general class function. So if chi1 and chi2 are not general class functions, then you can't do this, because then we don't know. For arbitrary class function, you can assign any value. So it's not necessary that at G inverse it will take value chi2 G bar. Yeah, but for characters this holds. So this sometimes I also denote it by this square bracket, this bracket. Yeah. Okay, so now note that we so this is a pairing which we will use to state and prove this orthogonality. So what we'll show is that if chi1 and chi2 are irreducible representation, then this pairing is either 1 or 0, depending upon chi1 equals chi2 or not. Yeah. But before that, let me state one sort of observation. So this we already saw. Home chi of home v2 v1 is chi1 chi2 bar. The second is you can figure out the dimension of the, see, G acts on V. So we can look at the space of invariance, subspace of invariance of G. So all vectors which are invariants under each action of G. So, so that's a vector space because, you know, it contains 0, and if it contains V, then it contains, and W, then it will contain V plus W and so on. So it's a vector space. And what we are going to show is that the dimension of this invariance you can compute using this character, the character of this representation. Yeah. So 1 over size of G summation chi G, G in G is same as the dimension of the invariance. So a priori, this is not even clear that it's an integer, yeah, because characters could be are just complex values functions, but we will show that this is. And this is indeed true. So let's so V is a G is a representation of G. Yeah. So then so this is if. Right. Yeah. So V is a representation of G, and then we look at this map. So the some 1 over size of G summation G in G. So each G from V to V is an endomorphism. Yeah. So if we sum them, then we again get an endomorphism of V, and if we divide by this number, we get an endomorphism of V. So first observation is that this is going to be an equivariant map. Now, is this clear why this is an equivariant map? Yeah, so some feedback in the middle will be great. Yeah. So is this clear why this is an equivariant map? So what you have to check is that phi. Yeah, so maybe I'll just write. So what one has to check is that phi of G dot V is same as G dot phi V. G dot phi V. But this is okay, yeah, because if you so left hand side is just 1 over size of G, and this you have to prove it for all G in G and all V in V. Yeah, so the left hand side is 1 over G summation maybe I should put G prime here, G prime in G, and G prime dot G dot V. Yeah, so that is what left hand side is. And if I just plug in the formula for phi in here, so G prime should act on G dot V instead of V. Yeah. And right hand side is right hand side is 1 over size of G summation G dot G prime in G of dot V. Yeah. So this I mean, and G is a fixed element. Yeah. So this sum will not change. Yeah. I mean, G prime dot G may not be equal to G dot G prime, but when you sum over all values of G prime, that sum is basically sum over all values of some element of a group, of all elements of the group. Yeah. So this is just and this is in fact same as phi V, nothing more. Yeah. So you can replace G dot G prime by G itself. Yeah. So it is G equivariant. And what in fact we will show is that it is it is a projection map. Okay. So So it's a projection map onto V sub G. Okay. So why is this a projection map? So to show that it's a projection map, what do we have to show? We'll have to show that if we take a vector which is invariant under all the elements of G, then phi V of V is V. And secondly, we have to show that image of phi is precisely V sub G, yeah, the invariance. So, so let's just check. So so if we take something which is invariant under the action of V, action of G, then of course G dot little G dot V is V, and so if you apply phi, then you get V. So this part is straightforward. Yeah, this follows from the definition of. So this part is straightforward, yeah, because G dot V is V. So you're just summing V order of G times and then dividing by order of G. So you get phi V is V. And second thing is to check that image of phi is indeed the invariance. So this formula is so that that is what happens. So you, for instance, so you take anything in the image of phi. So W is of this form, yeah. So 1 over G summation GV. Yeah. So if you apply G prime dot W, we just saw what we get is again this expression itself. Yeah. So G prime dot W is in fact equal to W. Okay. So we see that this is this image of phi is contained in the invariance. Set of invariance of G, and of course, set of invariance is phi is identity. So set of invariance is of course contained in the image. So that proves that phi is indeed a projection map. Okay. So now let's compute what is the trace of phi. Yeah. So remember the formula for phi is this. So if you calculate the trace of phi, so we'll calculate it in two different ways, and that will give us this formula. Yeah. So first, using the formula of phi. So trace of phi is just 1 over size of G, trace of each of these linear maps G. Yeah. But that trace is same as chi of G. Okay. Is this clear so far, or are there any questions? I hope it's making sense. Yeah. So if you have any questions at any point, please feel free to ask. So
sir, you have done phi of G dot B equal to G dot phi V, but here something phi V is come, but where G dot?
Say that again.
That G equivalent map, you have proved that phi of G dot B equal to G dot phi V. But G dot is not come, this comes out.
Yeah, the point is the sum G dot G prime, the sum with G prime in G. Okay, sorry. So the point is the sum G dot G prime with G prime in G. This sum is same as summation G prime in summation G prime in G. The sum doesn't change, right? These two sums are same, because what does multiplying by G do? It just permutes, yeah. So that's why this these two. So that's why you get that this is same as phi.
So G dot phi V also phi.
G dot yeah. So yeah. So this so if I put dot V here, we get the same answer.
Okay.
Yeah, because these two sums are same.
Yes, yes.
Yeah. So if I put dot V here, then I'll get the same answer. So that is what is used here as well. Yeah.
Yes, yes.
Same thing is used here as well. Okay. Any other questions or comments? So now you, so some of you may have noticed that now I'm not really using, so I'm using G to denote the the linear map as well. So last time we were using rho v G to denote the linear map, but here I'm just using the same thing. So I hope that doesn't lead to any confusion. Yeah. So I'm using the same notation for linear map and the elements of the group when there's only one representation. Okay, so this is the computation of trace in one way by using the formula. The other way is you think so v sub g is so phi is a projection onto this vg, yeah, and v sub g is a sub representation of G. It's a trivial sub representation of G. Yeah, so we can I mean, in fact, phi is G equivariant. So if we take W to be the kernel of phi, then we know that V is basically V invariance plus W. Yeah, direct sum W, and this is as representations they decompose. Yeah. But it doesn't matter whether it decomposes as representations or not. Now, if you think about, so we want to compute trace of phi. So how does phi act on V? On V sub G, its identity, and on this other piece W, it is the zero map, because that is W is in the kernel of phi. So if I want to compute the trace of this thing, what do we get? Is just the dimension. Yeah, so on this block it will be the identity matrix. On the block on this block it will be the identity matrix, and on this block it's going to be 0. So it is going to look like this 0 0 0. This is how the if you take a basis of v sub g and extend it to and take a basis of w and club them together to get a basis of v with respect to that matrix, if you take any of these elements of the group G, then it will and you consider this linear map phi, then phi is identity on this part and 0 on this part. So that is the matrix you get. So that tells you that the trace of phi is dimension of V sub G. Yeah. So that is and that is how why projections are useful, because then it becomes easier to compute the trace. Okay, so what we get is these two numbers are same, and that is what we wanted to prove. Yeah. So now now let me state the orthogonality theorem, which is one of the important theorem of this this lecture, and this we will use to study representation further. So it says that if V1 and V2 are irreducible representations of a group G, then this pairing is either 1 or 0, depending upon whether V1 is isomorphic to V2 or not. Okay. So of course, if V1 and V2 are isomorphic as G representation, so everything as G representation. So as G representation. Irreducible G representation. If V1 and V2 are isomorphic as G representation, then the characters are same, that we already know, and then this pairing will be 1. Otherwise, it will be 0. Okay. So let's try and see why this is true. So let's try to prove this. So remember, home V1 V2 is so if V1 and V2 are representation, home V1 V2 is also a G representation. Yeah, we saw that both in the lecture and then in the tutorial session. And if we look at those maps which are fixed by G, this is precisely the set of G equivariant linear maps from V1 to V2. So why is that? So what does it mean to say that so first of all, what is the action? Action of G on home V1, V2. So G of phi evaluated at GV is G dot phi V. This was the action. This is how, or maybe another way to write this was G phi evaluated at V is G dot G dot phi of G inverse V. Yeah, so this was the formula written down. Yeah, so if we the linear maps which are in, so if you want that G phi, so what are the elements which are fixed by each of which are in home V1 V2 sup G? So if we want to characterize these elements, these are precisely those phi such that G phi is equal to phi for all G in G. Yeah, where by G phi we mean these formula. Yeah, in this linear map. So G phi equals to so maybe this if and only if G belongs to maybe if and only if G belongs to home V1 V2 G. Yeah, and this is equivalent to saying that so G phi is equal to phi if we put it in this above formula, that tells you that phi of something. So yeah, this equal to sign. So something is overwritten. That's why it looks funny. Yeah. So maybe let me just rewrite this. So in the process of moving, this went crazy. So what it means is that G phi of V is phi. Yeah. So that tells you that. But by formula, G phi of V is G dot phi of G inverse V. That is same as G phi of V. G phi is same as V. That means G phi of V is same as phi of V for all G in G and for all V in V. Let's write it this way. Yeah. But that is same as saying that you replace. Maybe I should have used the earlier formula. But this is same as saying that phi G inverse V. This is equivalent to phi G inverse V is same as G inverse phi V for all G in G and for all V. Yeah, but this is precisely what it means to say that phi is G equivariant. Yeah. So I mean, instead of G inverse, one should put G, but that doesn't matter. Yeah, it's just reordering. So that tells you that phi is G equivariant. Okay. So every element of this guy is G equivariant, and anything any linear map from V1 to V2 which is G equivariant sits inside this. Yeah? So all these are equal. Okay. Now by Seus Lemma, if we take a G equivariant map between two irreducible guys, by Seus Lemma is either an isomorphism or it's zero. Yeah. So if V1 and V2 are isomorphic, then what does Seus Lemma say? So then yeah, so somehow this I don't know why things have moved a little bit here. So I'll have to erase this here. Yeah, so I'll rewrite this, whatever that is. So by Seus Lemma, if V1 is isomorphic to V2, then this must be one-dimensional. Yeah, I mean, it's any G linear map has to be an isomorphism, and there are not too many maps. Yeah, it's scalar times a multiple. So this is this home V2 V1 G is just one-dimensional. It's scalar times the identity. Yeah, so this is one-dimensional. And so what we get is that so home V2 V1. So the dimension. So now we will use the lemma which we just proved. So so the dimension of home v1, v2 raised to g, the invariant, is precisely this formula. Yeah. So this is what we proved. So for the invariance, we use this formula. Yeah, 1 over g chi of. So this is the representation for v. Yeah. So if we apply that formula here, what we get is this is equal to 1. Yeah, so it's written here. So this is equal to. So this is maybe a longer equal to 1 over g chi of home v2 v1 evaluated at g. But we know what is chi of home v2 v1 evaluated at g, because chi of home v2 v1 we know is chi1 g, chi2 bar g. Yeah. So we just copy it down, and that is, so it becomes 1 over size of g, chi1 g, chi2 bar g, and this is precisely the pairing chi1 chi2. Yeah. So if v1 is isomorphic to v2, then we get that this one is equal to the dimension of home v2 v1 g, which is equal to this thing. Yeah. And if v1 and v2 are not isomorphic, then we know that there are no non-zero g equivariant maps. Yeah. If v1 and v2 are irreducible, guys, the Seus lemma also tells here that there are no equivariant maps, no non-zero equivariant maps between. So that means this is the zero vector space, and hence this chi1 chi2 pairing, which by this calculation is same as dimension of home v2 v1 g is going to be 0. Okay, so this completes the proof of this orthogonality of the characters. Okay, any questions on this before I move on? Okay, so it's not a difficult proof. Yeah, it just need this observation and how the characters of this home looks like. Yeah. So let's see some consequence of this. Yeah. So now suppose V is a G representation. Yeah. Then we know that we can always write it as a direct sum of irreducible representation. Now we can show that that decomposition is also unique. Yeah. So then we can write it as V1 power R1 plus Vm power Rm, where Vi's are irreducible representations of G and Ri's are some number greater than 0. So we can write it as direct sum of irreducible representation, and I collect those which come with multiples. So maybe there are 2 copies of V1, 3 copies of V2, and so on. Yeah. So G may have certain number of irreducible representations, and you know, or whatever. So you can always club these together and write it this way. Now this is unique in the sense that if you can write V as direct sum of irreducible representation in this way, as I equals 1 to m prime Wi power Ri prime, then m prime must be m, and after some permutation, Vi must be isomorphic to Wi, and Ri must be equal to Ri prime. Yeah, so that is what. And how do you get this? Well, you know, you can write V as direct sum of irreducible representation like this, where Vi's are some irreducible representation, and you want to compute basically Ri for each irreducible representation of this. Yeah. So so what you do is take Wj as an irreducible representation of G. Yeah. Then what you do is compute chi Wj chi V. Yeah. So chi Wj chi V is, so V is direct sum of these irreducible representation. Then chi of V is just direct sum of is sum of these characters. Yeah? Because that is how character of the sum look like, is sum of the characters. And remember this this pairing is additive. So this is just a direct sum of I equals 1 to n chi Wj chi Vi. Yeah. And what is this number going to be? So if Vi is isomorphic to Wj, then it's going to be 1, otherwise it's going to be 0. So this is precisely the number of Vi's which are isomorphic to Wj for I between 1 and n. Yeah. So that number we call it Rj. Yeah. So what we get is V is just W1 per R1 to Wm per Rm, where and so these Ris are determined just from irreducible representation and the character of V. So this does not depend upon any choices. Yeah. So I hope this clears that it is unique. So in many representation theory book, they also write V as R1 W1 plus Rm W1 instead of this notation. So instead of this, sometimes they write that way. Okay. So both notations are there, but since I mean there can't be any confusion even if you write it this way. R1 times a vector space is there are not too many interpretations. Okay. So you can see, right, that if you are given a representation and you want to write it as direct sum of so you can so if you are given all the irreducible representation of the group, then you can figure out how the given representation looks like, how many copies of a particular irreducible representation is there, and so on, by doing this trick. Yeah. You pair it with the irreducible representation, the character of the irreducible representation, and the number you get is what you'll get. The pairing you'll get is a number, and that number is the multiplicity of the irreducible representation in that given representation. So as a consequence, what you get is if two G representations are, if you are given two G representations such that their characters are same, then they must be isomorphic. This is what I had promised you last time. Yeah, because if their characters are same, then what you get is that both V is isomorphic to W1 per R1 to Wm per Rm, where these Ris and Wi are determined just based on the character of V. And similarly, V prime is also isomorphic to this. So of course, then V and V prime must be isomorphic. So this in particular proves that characters determine the representation. Yeah. So two representation with the same character must be isomorphic. Okay, everyone. Any questions or comments?
Hello, sir.
Yes.
So if we have two representations for a group G,
yeah,
and those two representations are isomorphic, then can we say their characters are equal?
Yeah, of course. I mean, isomorphic representation means they are basically same representation. Yeah, these rho G's are the same. Yeah, so same linear map. I mean, they differ by maybe a conjugate. So they are similar representation. Yeah, so they exist a minute. So you basically are choosing a different basis in such.
Okay. So the corollary is nothing but it's just if and only if statement.
Yeah, because if part is, I mean, if two representations are isomorphic, their characters are same is trivial. Yeah. Okay. So it's the converse is the non-trivial.
Yeah. Okay, thank you.
Yeah. Any other questions or comments? So I guess I do right. So the justification I gave. So let W1 to Wm be all the irreducible representation of sub-representations of V plus V prime. Then what you do is take Ri equals chi Wi comma V, and that is same as chi Wi comma V prime. Then what we, by the above argument, we get that V is R1 W1 to plus Rm Wm, which is same as V prime. And hence they are isomorphic. Okay, so that completes the corollary. So there are many other observations which we can figure out. Yeah. So now suppose V is some representation, G representation. Then if we look at this pairing is going to be this number summation Ri square. Yeah, because if V is of this form, it has to be summation Ri square, because chi Wi comma chi Wj is 0. Yeah, if I is different from J. So I remember this pairing is additive in both arguments. So in particular, if you look at this pairing, it will always give you some non-negative number. Summation Ri square is some in fact positive integer. Yeah? Because so if you assume v is non-zero, then it will always give you some positive integer. So this positive integer will be 1 exactly if there is only one. So R1 is 1 and the rest are 0. Yeah. So in particular, so this is a positive integer and v is irreducible if and only if this pairing is 1. Okay. So that's another. So another way to characterize irreducible representation is you look at its character and do the pairing with itself. If you get 1, then it is irreducible. Otherwise it's not irreducible. Otherwise, you'll get some other positive integer. But it will be some certain sum of squares. So it could be any integer, but can't be 1. So this gives you another characterization of irreducible representation. Yeah. So this condition. Okay. So now we will use this to study the regular representation. As I said, that is our favorite representation. No? Regular representation. So let's try to understand how the regular representation looks like in terms of irreducible representation. So far we haven't even proved that there are only finitely many irreducible representation of a group G. So that also we will see. In fact, we'll give you an exact number of how many irreducible representation does G have later in towards the end of this this lecture. So. So let's first study this regular representation. So remember, regular representation V is Kg, yeah, and this character we know is the size of G when G is identity 0 otherwise, yeah. So if Vi is an irreducible representation of G, how many times Vi will occur in V? So to compute that, what do we have to do? We'll have to take the pairing of chi of Vi with V. Yeah, and this pairing is easy to compute because for most G it is 0. The at least one of the representation is 0, and only for identity it is non-zero. And for identity we know what is chi of Vi as well. Yeah. So this so what we get is. It is chi of Vi evaluated at identity times chi of V evaluated at identity, but that is order of G. And there is no other term because rest of the term will be 0 in that sum. Yeah. And then you divide by order of G. So what you get is chi of Vi of identity, which is same as dimension of Vi, which let's call is Ni, some number bigger equal 1. So that tells you that every irreducible representation of dimension Ni appears in the regular representation exactly Ni times. Yeah. So the Ni copies of Vi in V. Yeah. So that also tells you that there can be only finitely many irreducible representation. Yeah, because dimension of
Can you repeat this statement once? Just repeat this statement. Yeah, how many times?
So Vi. So I'll write it down. Yeah. So 1 second. Yeah. So this will vanish anyway. So what happens is in the regular representation Vi will appear Ni times. Okay, so Kg is N1V1 plus N2V2 up to NMVM. Or in the previous notation, what it means is that So kg is isomorphic to v1 power n1 plus vm power nm, where ni is dimension vi, and vi's are all irreducible representations of G. Vi, irreducible representation of G. Okay. So this is what the statement is. Is it okay? So what it says is that Vi appears ni times in kg. So this in particular also proves that there are only finitely many irreducible representations of G, because this V itself is finite dimensional, so there can be only so many irreducible representations. There cannot be infinitely many irreducible. Okay.
Yeah. Okay.
Yeah. Yeah. So we figured out how the regular representation looks like. So if G has a two-dimensional irreducible representation, then it will appear in the regular representation with multiplicity 2. If it has a one-dimensional regular representation, so remember in one of the exercises we showed that if we have a one-dimensional representation of any group, that appears as a sub-representation of G. Yeah. So now that is clear. Yeah, because any irreducible representation does appear as a sub-representation of Kg. In particular, one-dimensional. One-dimensional will appear with multiplicity only 1. Two-dimensional, etc., will appear with higher multiplicity. But so now that theorem, that problem, which was somewhat tricky, becomes straightforward if we do this abstraction. If we go through all this abstraction, that every one-dimensional representation appears as a sub-representation of this regular representation. Okay. Yeah, so I'm just restating this again. And from this, you can also observe that the size of G is sum of n1 square plus n2 square up to nm square. Yeah, because the dimension, you just calculate the dimension both sides. Yeah. So the dimension of the left-hand side is size of G. Dimension of v1 power n1 is n1 square. Yeah, because dimension of v1 is n1, and if you raise it, if you take n1 copies of it, then the dimension becomes n1 square. So if you compute the dimension, what you get is size of G is n1 square plus n2 square up to nm square, where n1 to nm are all irreducible, are dimensions of all irreducible representations of G. Okay. So that's another corollary we get out of this formula from 1. Yeah, and then if you this identity, this first identity, if you evaluate it at any element G different from, it's 2, you can also think of it as evaluating this identity at identity, this equation at identity element of G. Now, if you evaluate this equation at non-identity element of G, so you put some element of G which is different from the group identity, then what you get is n1 chi v1 G plus n2 chi v2 G and so on up to nm chi vm G. That must be chi of regular representation evaluated at G, but that is 0 when G is not identity. Yeah. So we get this corollary as well, this formula as well. So this is equal to 0 whenever G is different from identity. Okay. So I should box the whole thing. So is this clear? This corollary. So it basically, the first one is already seen, and 2 and 3 are just evaluating the first one. At identity, you get the second, and if you evaluate it at something not identity, you get the third. Okay. But I have still not told you how many irreducible representation does it have. Yeah. Okay. So is it? I mean, so from the group G, can we read out how many irreducible representation G has? So the next thing which I'll do will give this. Will provide this number. So we'll tell you what this M should be. Okay. So to do that, we need this theorem. So consider the space of all class functions on G. Yeah. So maybe I'll write it more explicitly. So H is functions f from G to C, complex values, such that f is constant on conjugacy classes of G. Conjugacy classes of G. Yeah, this is what H is. So of course, H is a vector space. If you take two functions which are constant on conjugacy classes of G, you add them, then it is again a function from G to C, which is constant on the conjugacy classes. So it's closed under addition, and is of course closed under multiplication over by complex numbers. So if you have such a function, you multiply by a complex number, you still land in this. Yeah. So H is this H is a vector space over C. Yeah. And we know that every character is inside H, because characters are class functions. Yeah. So it's complex values class function. And we also know that if you look at irreducible characters, then they are so on this class function we have that pairing which we introduced. Yeah. So we have this this pairing which we started with here. Yeah. And I said this pairing extends to the whole of class to all of class function. So on H we have this pairing, and with respect to this pairing, what we get is that these vectors, these irreducible characters are orthogonal. Yeah. So the previous theorem says that this irreducible representation with respect to this pairing is forms an orthonormal basis. Yeah.
It should be psi G bar, right? Not inverse.
Yeah, psi G bar. So on class functions, yeah, then it won't be linear. So let me just psi G bar. Yeah. So yeah, so I should put round bracket instead of triangle bracket. So in this proof, maybe I used this. So just replace this. Maybe I shouldn't have introduced the triangle bracket. So maybe this is same as that. Yeah. So let's not worry about. So just assume that this is same as this. Yeah. Let's forget about this G inverse part. So what we get is that these characters. So the theorem says that this form an orthonormal basis of this vector space with respect to this pairing. Okay. So it's a pairing. It's linear in the first, conjugate linear in the second. So it's a nice pairing on this complex vector space. And what we are saying is that it's an orthonormal basis. These irreducible characters of the irreducible representation. So we already saw that they are in the so by the above theorem we have already seen that the characters are orthogonal to each other, and their norm is 1. Yeah. So we already know that this set is an orthogonal set and their norm is 1. So all we have to show is that they span the whole of H. Yeah. So if we show that these irreducible characters span the whole of H, then we are done. That will prove that this is an orthonormal basis. Yeah. So we only need to show that they generate H. So to say that they generate H is equivalent to say that if we take any element F in H and suppose that element is orthogonal to all the characters. Yeah. So now I have put bar here. So maybe, so I'll just remove all these bars. So it's the round bracket. Yeah. So round bracket and triangle bracket are same. So. Okay, so I hope this is okay. So I'll change some places, but maybe I won't be able to. So equivalently, what we have to say show is that if F is orthogonal to all these characters, all the irreducible characters, so there's let chi1 to chi-r be the irreducible characters of be all the set of all irreducible characters of G. Then if it is if this pairing is 0, then if we prove that F is 0, this implies that F is 0. That means and this chi-i's do generate whole of H. Yeah, because if it doesn't generate whole of H, take something outside it. Yeah, then then the pairing is not going to be then I mean it will contradict this statement. Yeah. So what we have to show is that if we take an element F in H and its pairing with all the irreducible characters is 0, then F must be 0. So if you prove this statement, then that tells you that H must be generated by chi-i. Yeah. Okay, is that clear? So that we are reduced to this step.
Hello.
Yes.
So is this theorem is related to Brown-Smith orthogonalization?
No, it's not. No, it's not related to Gram-Schmidt orthogonalization. Is a method to get an orthonormal basis. Yeah. So it's not related to Gram-Schmidt orthogonalization theorem. Here we are already given a potential basis. Yeah. So we are given a we are given an orthogonal set, orthonormal set. We are asking whether it's a basis or not. Yeah. So what we want to do is just check that it spans the whole vector space. Yeah. So if it's not the whole thing, then you can find F such that the pairing of F with chi-i is 0 and F is still non-zero. But if I prove that if pairing of F with chi-i is 0 implies F is 0, that tells us that you can't find any F outside the span of chi1 to chi-r. Yeah, and hence this chi1 to chi-r spans H. Okay. Is it okay? Okay, so we are reduced to proving this, and to prove this we need a lemma. Yeah, so we are reduced to proving this statement, and to prove this we will use the following lemma. Okay, so it's again Seus Lemma kind of. So it again uses Seus Lemma. So everything. So remember, even in the orthogonality of characters, we use Seus Lemma. So here also is the same thing. So given a representation rho of G and a class function f on G, define this endomorphism, yeah, from V to V, which is Fg times G, or this time I've written rho G. So you define this endomorphism rho F to be Fg. Fg is some complex number, and rho G is a endomorphism of V. And you take the sum of these, yeah. So define this endomorphism rho F. Then the lemma says that if V is irreducible, then rho F is a scalar multiple. Yeah? And that scalar is given by this formula. So it's a scalar multiple of identity. Maybe I should get it that way. scalar multiple of identity. Okay. And and that scalar is given by, so you can calculate the scalar as well. It is 1 over n fg times chi vg. Yeah. Or you can write it in terms of this pairing. So, so I'll use this notation again. So in terms of this pairing, it's just this. Yeah.
So here it will be bar, right?
No, in the round bracket, we don't put bar. The formula itself has bar in. Oh, yeah. Here it is bar. You're right. Here there should be a bar. Okay. Yeah. Chi v bar, chi vg bar. Yeah. Okay. Yeah, so yeah, so I should yeah, but it doesn't matter. Yeah, so maybe I mean, to say that f is 0 is equivalent to saying that f bar is 0. Yeah. So okay, so maybe I'll adjust a little bit. So this is yeah, so maybe I'll change the formula a little bit. Chi v comma f bar. Yeah. Chi v comma f bar. So now it is okay. Yeah. So lambda is this, and this formula. So this is okay. And here n is the dimension of this vector space V. So let's see the proof of this lemma, and then once we know the proof of this lemma, we will come back and complete the proof of this this statement, that if f comma chi I is 0 for all I in for all irreducible representation, then so maybe here also I may have to change. So I'll just say prove that chi I comma f is 0, then f must be 0. Okay. Okay. So let's see the proof of this thing. So first thing is that this rho f is equivariant, is G equivariant map. So it's the same trick, yeah. So first check that rho f is G, so because we want to apply Seus lemma, yeah. So first check that rho f is G equivariant. And so to prove rho f is G equivariant, what do we have to prove? We have to prove that rho f G dot V is same as G dot rho f V for all V in V and also for all G in G. We want to prove that rho f followed by rho G, this composition, is same as rho G composed rho f for all G in G. Yeah, so sort of looking at as maps, endomorphisms of V. Yeah, and if we multiply by rho G inverse both sides, what we have to show is that this is true. All the three statements are equivalent. So all we have to prove is this identity to prove this claim that rho f is equivariant. So let's try to verify this identity. So what is left hand side? Left hand side, we just plug in the formula for rho f. Yeah. So rho f, remember the formula is fg times rho g, summation g in g, fg times rho g, where fg is just a complex number. Yeah. So if you do that, what you get is fg prime comes out, and you get summation g prime in g, rho g inverse, rho g prime compose rho g. So fg should be in the middle, but fg is a scalar, so we can pull it out. Yeah, and we get this. And since rho is a group homomorphism, this is same as rho G inverse G prime G, yeah, times Fg prime. But Fg prime and Fg inverse G prime G are same because F is a class function, yeah. So remember, F is a class function. So G prime and G inverse G prime G are of course conjugates, yeah. So what you get is the sum is same as summation Fh rho h, where h is G inverse G prime G, yeah? And summing over all G prime in G is same as summing over all h in G, yeah. But this is and this is precisely rho f, yeah, which is the right hand side. So we see that so that proves that rho f is indeed G equivariant. So once rho f is G equivariant, we can apply Seus Lemma. So see, this is an endomorphism of V. Yeah. So rho f is a map from V to V, and it's an endomorphism. So Seus Lemma says that rho f must be scalar times identity. So let that scalar be lambda. Then we want to compute this lambda. Yeah, that is the last part of this lemma. So what is that lambda? Lambda is that you can express it in terms of trace of rho f. So trace of rho f is going to be n times lambda, where n is the dimension of P. Yeah? Because rho f is lambda, so it's lambda times identity. So and on the vector space V, so the trace is trace of this matrix, which is lambda, lambda, lambda on the diagonals. Yeah, so you get trace of rho f is n times lambda. And if you use the formula for rho f, then you can again get another. So rho f is this function, this endomorphism. So you can use this formula to also compute trace of rho f. So that is the second way to compute it. So trace of rho f is trace of this sum, and trace of this is you just so fg is just a number, and trace of rho g is precisely chi g. So you get this thing, yeah, fg rho g bar, which by definition is this thing, which is same as so maybe I'll write it like I did there, chi f bar. Yeah. In terms of round bracket, sorry, size of G is also there. Size of G times chi f bar. Yeah. So now if you equate n lambda with this formula, what you get is lambda is G over n times f of chi bar, which is same as size of G over n f bar chi. Sorry, chi f bar. I want linear in the first. So I don't want to use chi bar because I want to say orthogonal to characters. It doesn't matter, it's just some something because I. Now let's go back to the theorem. Yeah?
F bar.
Chi f bar, yeah. Yeah. Now let's go back to the theorem. So so suppose chi f is 0 for. So what do we have to prove? So if chi f is 0 for all I between 1 and r, then we want to conclude that f is 0. So let me just edit this part a little bit. Now going back to theorem, since okay, I have to erase this. Chi I f is 0 for all irreducible characters. This also means that chi I f bar is also 0. Yeah. Because the formula just, I mean, yeah. So maybe what we'll show is that f bar is 0, but f bar is 0 implies f is 0. Yeah, so let's just write it this way. Just keep it this way. So let's just forget. So suppose chi comma f is 0. Yeah, where f is some class function. Yeah. So, so this pairing is same as is for all irreducible characters. Yeah. Then it is true for all representation, because any representation you can break it as sum of irreducible representation. So this tells us that this pairing is 0, chi b, f is 0 for all representation v of g. Yeah. So then what do we know about rho f? Then this rho f is this guy. This must be 0. Yeah, because rho f is some scalar times identity, and that scalar is precisely this number. Yeah, chi f bar. Yeah. So if this number is 0, that tells you that rho f is rho f is this guy, which is 0 for any representation v of g. Yeah. Is that okay? So maybe to be consistent, let's just put f bar here. So since chi f bar is 0, we will prove that we will prove that f is 0. Yeah, and hence f bar is 0. So if f is 0, if and only if f bar is 0. Yeah, so we get that rho f is so by the lemma we know that rho f must be the 0 map. Rho f is a scalar multiple, and that scalar is given by this formula, and that formula is some multiple of this thing, which is 0. Yeah. So we get that rho f is the 0 endomorphism, and this is true for any representation. So here this rho v, I can put any v here. Yeah. So for any representation, we get that this is 0. So in particular, we can take v to be the regular representation and see what we get. Yeah. So if we take v to be the regular representation, then rho f is fg times rho g, where rho kg is g, regular representation. And if we compute it, so the reason we are looking at regular representation is we know what this guy is. Yeah. So now if we evaluate it at identity, this guy, then what we are doing it, we know that the rho f is 0, so we get 0, and rho f evaluated at identity is 0. So why am I writing it this way? So rho f evaluated identity is 0, and if you
so in the sum, it should remain only one term g.
Yeah.
It should be the mod g delta g. The delta is the delta.
Yeah, sorry. So what I meant was rho f is an endomorphism. Yeah. Yeah, this is okay. Yeah, so rho f is a map from v to v, kg to kg. Yeah, so this is how you think of it, kg to kg. Yeah, and so if you evaluate rho f at e, then what are we doing? So how does the action? How does this act? Rho g of kg is multiplication by g. Yeah, so it's is g evaluate g times identity. Yeah, in v, which is same as kg. Yeah, and that is 0, right? So g times identity is just g. So what we get is 0 is same as summation fg g in kg. So but this g in g, this is a basis. Yeah. So the elements of g, they said g is a basis of kg. Yeah. So that tells you that all the coefficient, these fg's must be 0. Yeah, so which implies that this function f, f must be 0. Okay. Is that okay? So maybe I should, one has to prove, put f bar everywhere. And so you get f bar g is 0, which means f is 0 as well. Fg is 0. Okay. So we have proved that if the pairing with so this equivalent, so we had reduced the theorem to proving that if the pairing with every irreducible character is 0, then f must be 0, and that is what we proved here. Yeah. So that completes the proof of this theorem that H is generated by these this orthonormal basis. Okay. Is this okay, guys? Or if you have some questions, since the proof I did it in sort of 2 steps, meaning I inserted a lemma in between. So maybe I'll let you ponder over it a bit, and if you have some questions, you can ask me. So first, you think of this lemma, which says that if you cook up this this endomorphism using this function, using this class function, then that endomorphism is just multiplication by lambda, which is given by this formula. Okay. And then you use that to prove, to show that if chi I f bar is 0 for all irreducible characters, then f must be 0, and hence f bar must be 0. Yeah, so actually there shouldn't be this, this bar shouldn't be. So in the formulas there are no bars, only in the symbol there is. So that proves that Fg is 0 and hence f bar is 0. So f bar is 0. Okay. So I hope this yeah, say that again.
The screen is not visible.
Oh, the screen is not visible. Oh, okay, sorry. Somehow stopped sharing. Okay, is it okay now?
Yes.
Ah, good. So any questions on this thing? Okay, so now what I want to do is use this to prove a corollary. So I wanted to tell you how many irreducible representations are there. Yeah. So the number of irreducible representation is same as the dimension of H. Yeah. So corollary is so maybe so corollary. Let G be a finite group. Then the number of irreducible representations of G is same as the dimension of class functions, dimension of space of class functions on G. Space of class functions on G. And what is the dimension of space of class function on G? What is this number? So dimension of space, so class functions are supposed to be constant on each conjugacy class. Yeah. So it's basically for each conjugacy class, you can take any complex number. That is what this this vector space is. Yeah. So on each conjugacy class, you can take any complex number. That is the only restriction. So this dimension is basically same as number of conjugacy classes of G. Conjugacy classes of G. Yeah. So this H, this space H is basically C plus C plus C as many times as the number of conjugacy classes. Yeah. So that that vector space has dimension precisely same as conjugacy classes. Yeah. So you see the number of irreducible representation same as the number of conjugacy classes. So that is what we have proved now. Okay. So maybe I'll stop here, and next time we will do some examples. Okay. So we haven't really done any examples. So next time we'll compute all irreducible characters of certain groups. So next time, so for abelian groups, it's pretty straightforward. But for maybe S3, so example, we will see maybe S3 and maybe DN, this dihedral group D2N, maybe. These examples we will see next time. Compute all the irreducible character. And see if you, so that is all we, so if you want to study representation of a particular group, if we know all the irreducible character, then we know everything. Yeah, any representation can be written as dx sum of these irreducible representation. So we can write down all representation in that spirit. And and in fact, if you are given any sum, so if by some magic you got some representation and you want to know what this representation is, then you just have to compute its character, and then you can figure out what that representation is. So how many copies of a particular irreducible representation is there? If you know all the irreducible characters or of G. Yeah. So it is a so upshot is that it is important. It is important to calculate all irreducible characters of a group. Irreducible character means character of irreducible representation. Yeah. So this is what. So if we know this, then we know everything about that group's representation. So this is what we will try for some small groups next time. Yeah. So maybe I'll stop here, but I'll leave the remaining 7 minutes or 6 minutes for questions and answers. So maybe we can pause the recording for questions and answers. I don't know how to pause it, but maybe someone else can pause the recording.